Learn calibration. Description. Explain in detail. Calibration refers to the process of adjusting the outputs of a machine learning model to better align with the true probabilities of the events being predicted. This is particularly crucial when dealing with probabilistic models, such as logistic regression or support vector machines, where the model's outputs represent the probability of a particular class or outcome. Calibration ensures that the model's predicted probabilities accurately reflect the likelihood of the event occurring in the real world. Inputs. Input 1. Explain in detail. The input to calibration is a trained machine learning model, typically a probabilistic model like logistic regression, support vector machines, or a decision tree. This model should have been trained on a labeled dataset and is ready to make predictions on unseen data. Input 2. Explain in detail. Additionally, a set of labeled data is required for calibration. This data should be independent of the training data used to train the original model. It serves as a reference point to adjust the model's predictions based on its performance on this new dataset. Outputs. Output 1. Explain in detail. The calibrated model itself is the primary output. This is the adjusted version of the original model, where its predictions are recalibrated to align better with the true probabilities of the events. Output 2. Explain in detail. The calibration process often provides various metrics that measure the quality of calibration. These metrics quantify how well the model's adjusted predictions match the observed probabilities in the calibration dataset. Common metrics include Brier score, calibration plots, and reliability diagrams. Steps. Step 1. Explain in detail. The first step involves obtaining predictions from the original model on the calibration dataset. The model generates predicted probabilities for each data point in the dataset. Step 2. Explain in detail. The calibration step adjusts these predictions based on the observed outcomes in the calibration dataset. This adjustment can be achieved using various techniques, including Platt scaling. Fits a sigmoid function to the original model's predictions, mapping them to calibrated probabilities. Isotonic regression uses a monotonic function to adjust the predictions, ensuring that the calibrated probabilities are non-decreasing as the original model's predictions increase. Histogram binning divides the predictions into bins and adjusts the probabilities within each bin based on the observed outcomes in that bin. Metrics. Metric 1. Explain in detail. Brier score. This metric quantifies the mean squared difference between the predicted probabilities and the actual outcomes. Lower Brier scores indicate better calibration. Metric 2. Explain in detail. Calibration plots. Visualize the calibration by plotting the predicted probabilities against the observed probabilities. Ideally, the points should lie close to the diagonal line, indicating good calibration. Visualization plots. Visualization plot 1. Explain in detail. Calibration plots. These plots are essential for visually assessing calibration. They depict the relationship between the predicted probabilities and the observed frequencies of the events. A well-calibrated model would have points close to the diagonal line, indicating that the model's predictions align with the true probabilities. Visualization plot 2. Explain in detail. Reliability diagrams. Similar to calibration plots, these diagrams illustrate the calibration performance. They show the average predicted probability for each bin against the observed frequency of events in that bin. A well-calibrated model would have points close to the diagonal line, suggesting that the model's predictions are reliable across different probability ranges. Fine-tune parameters. Parameter 1. Explain in detail. Number of bins when using histogram binning. The number of bins significantly influences the calibration. Too few bins might not capture subtle variations in the model's predictions, while too many bins might lead to overfitting the calibration data. Experimenting with different numbers of bins is essential to achieve optimal calibration. Parameter 2. Explain in detail regularization parameter in methods like isotonic regression. A regularization parameter controls the smoothness of the calibration function. Higher regularization values make the calibration function smoother, preventing overfitting to the calibration data but potentially sacrificing the accuracy of calibration. Uncertainty methods. Uncertainty method 1. Explain in detail confidence intervals after calibration. It is possible to estimate the uncertainty in the calibrated probabilities by constructing confidence intervals. This provides a range within which the true probability is likely to lie, giving a more complete picture of the model's prediction. Uncertainty method 2. Explain in detail Bayesian calibration incorporating prior knowledge about a model's parameters through Bayesian methods can provide uncertainty estimates. This approach allows for capturing the uncertainty in the model's predictions and the calibration process itself. Challenges and fixes. Challenge 1. Explain in detail limited calibration data. Insufficient calibration data can lead to inaccurate calibration, especially when the data is not representative of the true distribution of the events. Sample use case that resulted in Challenge 1. Imagine a model predicting the probability of a customer purchasing a product. If the calibration data consist mainly of customers who have already purchased the product, the calibration might be biased towards overestimating the purchase probability. Fixes to Challenge 1. Collect more calibration data. Gather a larger and more diverse dataset that reflects the real-world distribution of events. Use synthetic data. Generate synthetic data based on the existing data to augment the calibration dataset. Employ transfer learning. Leverage a pre-trained model that has been calibrated on a larger dataset to improve calibration with limited data. Challenge 2. Explain in detail overfitting to the calibration data. The calibration process might overfit to the specific calibration dataset, leading to poor performance on unseen data. Sample use case that resulted in Challenge 2. A model calibrated on a dataset with a specific distribution of events might perform poorly on a dataset with a different distribution. Fixes to Challenge 2. Regularization. Introduce regularization techniques to the calibration methods to prevent overfitting. This can involve using penalty terms that discourage complex calibration functions. Cross-validation. Perform cross-validation on the calibration dataset to evaluate the performance of the calibrated model on different subsets of the data. Use a simpler calibration method if overfitting is a concern. Consider using a simpler calibration method like Platt scaling instead of more complex methods like isotonic regression. Challenge 3. Explain in detail choosing the right calibration method. The choice of calibration method can significantly impact the calibration results. Some methods might be better suited for certain types of models or datasets. Sample use case that resulted in Challenge 3. Platt scaling might not be appropriate for models with high dimensional output spaces, while isotonic regression might be more suitable. Fixes to Challenge 3. Experiment with different methods. Try different calibration methods and evaluate their performance using appropriate metrics. Consult literature. Refer to research papers and documentation to understand the strengths and weaknesses of different calibration methods and their applicability to specific scenarios. Consider domain expertise. Incorporate domain expertise to guide the selection of the most appropriate calibration method for the task.